Hello, Calculus 2 students. I am back in Euler. Sorry that you're not here with me, but I'm going to go low tech and use the dot cam to record me going through the workbook so you can go along with me here. So we were going to do 9.5 next. That'll be our first virtual session here. And we're not going to do plickers, obviously, but we can talk about this problem. And the problem was if x is an unknown constant here, which test would you use for this series? So it has an n. Like before, it's an infinite series, but it has this extra variable, which is really fixed, so we're going to call it an unknown constant. And the problem is that we don't know what x is, so if you look at x minus 2 right here, I don't know if that's positive or negative. If x is 3, that's always positive. If x is 0, it's alternating, right? Sometimes positive, sometimes negative. The comparison test needs positive terms, so that's out. The alternating series test needs, to alternate, and you don't know if it does. So it's definitely not all of the above. And you also might have figured out it was the ratio test because of n factorial, but don't forget the ratio test also plays well with x to the n, and we have this minus 2 we'll talk about later. But in general, when you have what we're going to call today power series, there's going to be some coefficients, cn or an, and then you're going to have x to the n, or maybe something like x minus a to the n, something there. It's going to look like these. These are what we're going to call power series. And so that x to the n is kind of a geometric piece, and that's why we're going to use the ratio test. Throughout all these problems today, I'm going to always start with the ratio test. We'll use everything else from Chapter 9 as well, but we'll be using the ratio test a lot. Okay, I'm going to make a separate video here with Desmos to show you some tricks, but right now I'm going to do this old school with the workbook, and you're going to see a sequence of graphs here. What we're changing with this x value is that this series now has an idea that when you plug in x, if the series converges, it converges to a number. So you input an x, you get out a number. That's what a function is. So we're going to create functions out of series, and this is what we're going to call power series. Functions have domain. They only work sometimes, right? Maybe. So we're going to start with this, basically this function, this power series, and we're going to figure out which function we're modeling and when does this work. So if you look at these graphs, the first one is 1 minus x squared. And then what they did is they added x to the fourth as an extra term to get the next graph. And then when you subtract x to the sixth, you get the next graph. If you add x to the eighth, the next one. And then last, if you subtract x to the 10th. So there's a pattern here, and then each graph would change. If you plug these into Desmos, which we'll do later, you'll see each graph appear as you go up the line. And so the idea is that we're going to keep doing this forever. This is the beginning of the series, but remember, these are infinite series we're talking about. Okay, so first we want to know for which x values do the y values not really change? So that's question one. If you look here, these are always the same thing, right? Kind of around the middle. So I'm going to roughly say from minus 1 to 1. If you guess slightly differently, that's okay. We'll check the real answer later. But basically around 0, and 1 is just an easy number to use. We're just guessing now. Now, everywhere else, the y values seem to get huge and also change, right? They're going up, they're going down, they can't decide. That's everything else. So minus infinity to minus 1. And then you can write union here, or you can just write and 1 to infinity. And I guess 1 should be doing something, so maybe we'll close off 1. We're not too concerned about that. Okay. The next part says, I claim this function is a geometric series, something to the n. What's the ratio r? So remember, it was always a r to the n. A is the first term. A is 1 right now, right? So let me write that down. A equals 1. So a equals 1. R, what are you multiplying by each time to get the next term? Negative x squared. So that goes here. All right, so negative x squared is the r. When do geometric series converge? They converge when the r is less than 1 strictly in absolute value. So I want to solve that. X squared is always positive, and the absolute value kills the negative, so I really only want to solve this. You can graph x squared. You can think about this however you want. If I want to square a number and stay small, less than 1, it's got to be less than 1 to start. So x needs to be from minus 1 to 1 open, or you could say minus 1 to 1. Which makes sense. This series only converges where the graphs up there are being consistent. Where the graphs are being crazy, this thing diverges anyway, this series. So the series won't be helpful outside of minus 1 to 1. So question 4 kind of matches what's going on with questions 1 and 2. All right, don't forget for geometric series, we're really lucky that we can add these up. Notice that there's no a in this expression because a is 1 right now, and r is minus x squared. So this series, this minus x squared to the n, should be 1 over 1 minus negative x squared, which is 1 over 1 plus x squared. And you should recognize that function. That is the derivative of arctangent, right? The next part says graph your function from the previous question. We will do that in Desmos here in a bit, but you should know the graph looks like this. So this is not arctangent, but it's derivative. Looks like that. And this matches up with the graphs you can see at the top of the page here, only from -1 to 1. It does seem reasonable there. Obviously, it's not reasonable where the series diverges. Right? The series should be flattening if it wants to look like this, but they very much disagree outside of -1 to 1. Going to the next page here, we need some definitions, and they're kind of just thrown at you here. So I'm going to be pretty thorough here, and there's not a lot of space for 7, 8, 9. So I'm going to get some scrap paper here in a second, and we're going to go through these in great detail. Okay. So the example above it says the radius of convergence is 1, the interval of convergence is -1 to 1. And showing the endpoints is not in the interval is actually pretty hard, but this time we cheated and used the geometric series. We're going to now do the ratio test on the next 3 problems. But first I want to clarify about radius of convergence and interval of convergence. If you think about that previous graph, so let me draw it again up here. It was centered at 0 in the sense that the stuff that worked, 0 was in the middle. And I'll talk more about having the center not be 0 here in a minute. 7, 8, 9, the center will be 0 every time. We were able to go 1 each direction, and that's the stuff that worked, right? And then from -1 to 1, that was the interval. The intervals can change. You'll see here in a minute they can be a little bit different. So for that previous problem, for that was questions basically 1 to 5, the r was 1 and the I for interval, so an r for radius, was -1 to 1. And the I is basically the domain of the series as a function. So now that the series has a variable, it's a function of x, and the I is basically the domain. And the r is just a shorthand way to think about the domain, because it's always going to be symmetric around the center. You're always going to have a center and go both ways. And I will show you that with these 3 problems. So because these 3 problems are going to require more space than we have here, I'm going to do it on a scrap piece of paper. That's why your workbook has that space on the side where you have a blank page. So if you're following along in the workbook, go ahead over there. So here's a blank piece of paper. And first, let's do x to the n over 2n squared. So I'm going to do the sum. And the way I'm going to do that is I'm always, for these problems, I got lucky the first time with the geometric series, but I'm always going to do the ratio test now. So I'm going to take the limit as n goes to infinity, x to the n plus 1 over 2 n plus 1 quantity squared, times, I'm going to do the reciprocal, then 2n squared for an. Now, I always want to use the ratio test because the x's are always going to cancel real nice. Remember that the ratio test plays with geometric series very well, so that's why I'm doing that. The 2's cancel as well. There's a lot of ways to think about the next part. We were pulling stuff out before, but you can also think of absolute value x as a coefficient. It's the leading coefficient of the top. This is a limit with n, not x, so x is a constant. And then if I follow the bottom, I really just need the first part. You want the ratio of the leading coefficients because they're both n squared. So that limit's going to be absolute value x. Now, these limits for this section are going to come out with variables. And you know the ratio test wants, you want this to be less than 1, right? So when is that true? Well, that's from -1 to 1. But I don't know about equal to 1, right? So if this limit came out equal to 1, if x basically was 1 or -1, I don't know from the ratio test. I need to do something else. So we already know that it's from -1 to 1. If we draw the number line, here's 0, here's 1, here's -1. We know it's this. We don't know about the endpoints. We don't know if we want open or closed circles on the end. But you can tell from that picture the radius is 1. Basically, when you get absolute value x less than something, that's usually the radius. It's pretty easy to tell. If you're unsure, just draw the number line. Just think about it. So what we're going to do now is, because we need to know about 1 and -1, because before we had the rule about geometric series that we use, and now we need to do something different, we're going to plug these in for x. to check if those individual points work. And we're never going to have to check more than the two endpoints. So if x equals 1, I plug that back into the top series. I have 1 to the n over 2n squared. Well, 1 to the n is just 1. And you can tell that that's a multiple of a convergent p series, right? P equals 2, it's bigger than 1, so that's convergent. Okay? What that tells me up above is that 1 counts, close circle, close bracket. If I go to the other side and I make x minus 1, that tells me that I have minus 1 to the n. So now it's alternating. And I can do this a couple ways. I can use the alternating series test, or I can just say, hey, the absolute value of this, so this is the test for absolute convergence, is the previous guy which converged. So this is convergent by the absolute test for absolute convergence, or by alternating series test, whatever you want to do. Just know that if it works, it's definitely going to work when you add alternation, right? So I can close this dot, I can make this closed. Okay, so first time we had open, open, right? Now it's closed, closed. So this graph, I'll show you later, of this power series, will work at its endpoints, but only from -1 to 1. And it'll converge to some picture, some graph. Okay, so this one then, that's my interval, is -1 to 1. Okay, so that was number 7. Now I'm going to get out another piece of paper, and we're going to do number 8. And save some space because after 8 and 9, we're going to do a few bonus problems. All right, so now we're headed to 8, which, same idea, this series is x to the n over n2 to the n. And what I want to do here is the same exact idea. We're always going to start with the ratio test. So this is going to be x to the n plus 1 over n plus 1, 2 to the n plus 1. And then reciprocal of that, just with the n's, the a-n's. Take the absolute value, take the limit. And lots of nice things cancel. The x's die, except 1. The 2's mostly go away. N and n plus 1 don't cancel. We're going to think about this like before. I still have 1, 2 on the bottom. Here's my limit. Okay, I could distribute the 2, but you know it's 2n and then absolute value x times n. So the ratio of the leading coefficients is this. And I want that to be less than 1. Now, you don't want to say the radius is 1 yet. You don't want to stop because you want the radius to be just absolute value x by itself. And if you're confused about this, you really should just get x alone, absolute value x, and then think about number line, absolute value stuff way back from when you did that in junior high or early high school. So if you do absolute value x is less than 2, well, that means we're still centered at 0, and I'll show you one here in a minute that's not centered at 0. This is a number line, not a graph. So here's 0, here's 1, here's 2, minus 1, minus 2. So I want to go 2 each way from 0. So that's here and here. Or you can write it like this if you learn how to do that with inequalities. But either way, you can tell that the radius is 2. I'm going 2 each way from 0. What I don't know yet is I don't know about the endpoints. So I have -2 to 2 for the interval, and I need to figure out the endpoints. Just like the previous problem, I'm going to plug those in. So let's start with x equals 2. I just like to do the negatives last. So x becomes 2. The 2 to the n's cancel, and it becomes 1 over n. And you know that that's divergent. That's the harmonic series. P equals 1, and you really need p greater than 1 for this to work. So that's not going to be any good. So I want an open bracket there. Now, if x is -2, the top is getting a little weird. It's -2 to the n over n2 to the n. And now we got to do a little bit of an algebra trick here that's going to be feel weird, but it's not too big a deal. Think of -2 as -1 times 2. It seems small, but when you do that, now when you think about the power on top, I'm going to take the power of each individually, and then I'm going to cancel the 2 to the n's. What's important is you need to know that the top now is not -1. You're going to be very tempted to just have -1. It's -1 to the n, and you don't see that easily if you don't do that step. Okay, so that's an alternating harmonic series, and that's the one that we actually showed was convergent, conditionally convergent, but convergent. So this converges by the alternating series test, and that means way up here I want to close that bracket. So that side works, not the other side. So we've had open on both sides, closed on both sides, closed on one side out of those three problems. All right, so that's number 8. We got our radius, we got our interval. Let's go ahead and go to number 9. Okay, so number 9 is 2x to the n over n factorial. And I'm going to do the ratio test yet again. So 2, not x plus, n plus 1, and then over n plus 1 quantity factorial. Do the reciprocal for an, absolute value, take the limit, all those fun things we get with the ratio test. Cancel our x's like we have been. Now remember, the factorial cancels different. It's n plus 1, then n, and then some stuff, and this is n and some stuff. So it all cancels except for the n plus 1. So, and of course the 2's cancel. So I get absolute value x up top, n plus 1 on bottom, everything else cancel. Remember that the limit is an n, not x. So x is constant, and n is growing huge, which means this goes to 0. Last time I checked, 0 is always less than 1, so this looks different than the other problems. The other problems had you kind of finagle which x's worked. This seems to indicate that it doesn't matter what x is, this graph works. Well, okay, well that is possible, and what that means is that the radius is infinite, and the interval is the whole line, minus infinity to infinity. So when we graph this later, you'll see that this function, the Taylor series, converges everywhere. This function's domain is all reals, which is good. That's an ideal situation. You'll see that we're really focused later on graphs that do that, the power series that do that. Okay, so we had open intervals, closed intervals, half open. We had the whole line. There's one more thing that can happen, and that's it. So we'll call this 9.5. And then we'll have a 9.75. I'm going to sneak in some extra problems here. So what if we did the exact same problem, but we had 2x to the n times n factorial up top, still going from, what they have, 1 to infinity. I haven't really been drawing the 1 to infinity, but it's not too important. I'm going to do the exact same stuff with the ratio test, although you should already be able to tell the terms don't really go to 0, but there's a little subtlety here that I want to show you. So this is 2x to the n plus 1 factorial. That's not a fraction, so I can do all this without any reciprocals. 2's cancel, most of the x's cancel. These become just n plus 1. So you get this limit, you still got absolute value x. Then you have n plus 1 on top this time, which is bad, right? This thing blows up, this should be infinity, unless x equals 0. If x equals 0 here, this whole thing has already become 0. And then there's nothing to do with the limit 0. So this is a terrible series that really doesn't matter. It doesn't converge at all except at one point. So we would say that the radius is 0 and that the interval is just the point 0, just the center. And here in a minute we're going to talk about, for just a minute, there's a theorem on page 493. It's kind of awkwardly worded, but we'll talk about the centers here in a minute. This is going to help. This is what I'm trying to tell you, that there are only 3 scenarios. So this is about radius relative convergence. So they have this idea of the CN, they have an x minus a. We haven't had the a yet, right? Our centers have been 0. We're going to do that in a second. But we said use the ratio test. If you get an infinite limit, the radius is 0. You only get the one center spot. If you get 0, the radius is infinite. We just did one of those. If you get some expression, and theirs is kind of convoluted, all you really need to know is that you get a radius. This is kind of convoluted looking. You don't need to memorize this. You're just going to solve for this x minus a expression, and then you're going to work it out. You don't need to memorize this weirdness. But you're going to get some actual interval with endpoints, maybe open, maybe closed. So basically all that matters is you either get 1 point, everything, or some interval. All right, so let me show you an example where the center is not 0. So I'm just going to make one up. I'm actually just going to maybe shift one of the ones we already did. So let's move that page. Let's go back to 7, and let's just change it. Let's make the center 2, which is that's what it looked like on your Pookish problem. So let's come here. Okay, so this is kind of like, let's call this 7 redux, and this is 9.75. And then we'll get to problem 10. Okay, so I'm going to make this still 1 to infinity, and it's going to be x minus, we'll use a different, well, we'll use 2, I guess. X minus 2 over 2 n squared, and I want to know the radius and interval here, okay? Doing this kind of shift shouldn't change the radius, but you'll see how the interval is going to look different. So I'm going to do the ratio test again, so limit and goes to infinity, have some value, and I want x minus 2, the n plus 1, 2 n plus 1 squared, and then do the reciprocal of the original. And things cancel like before. It's the x minus 2's that are all cancel except 1. The 2's cancel. You can think of x minus 2 absolute value as a fixed number. That's the coefficient of n squared. And then n squared on the bottom has coefficient 1. So this is going to be absolute value x minus 2 over 1 is the limit. Okay? So absolute value x minus 2. This still works like before. It's less than 1. And that's going to show you right here that the radius is 1 because it's the absolute value stuff less than something. But I'm still going to work it out because you still want to know the interval. And you'll see the radius is when you do this. So probably most of you learned that, hey, when you have an absolute value like this, you should do this. The reason why you do that is because this is technically distance on the number line. So x and 2 are within 1 of each other. So if you go to 2 on the number line, 2 is the center. So this number here, whatever you're subtracting, is the center. If you're adding 2, the center would be minus 2. But for us, here's 0, here's 1, here's 2. So I'm going to go 1 each way, so it's this region. If you add 2 here, you'll see that. I'm going to go between 1 and 3. And so my radius is still 1. Right, because I'm at 1 each unit each way from 2. But my interval is not between minus 1 and 1, it's between 1 and 3. And I'm not going to do all the same stuff again. You'll get exactly, if you plug in 3 and 1, you'll get exactly what we had before, and you'll close the endpoints there. So you'll get a closed interval from 1 to 3, so you get a different region because you basically shifted the power series. So that's what it looks like when they're off center. All right, so now I'm going to go back to the worksheet. And I want to talk a little bit about applications, which of course math means applications to other parts of math. But I'll show you a little bit about why we care about these things. So the next part says why. You ask, do we care? And so at the very beginning of this lesson, we did the arctan derivative. And so we're going to integrate both sides here. But you know that's arctan x because you did your gateway. On the other side, the advantage of these power series is that I can always use the power rule. So polynomials are the easiest thing to integrate. I just use the powers. X to the 5th, because I go up 1. And I keep going forever. And then that's the idea. Now I have a power series for arctangent, which is pretty crazy, right? I had a series for its derivative. Now I have a series for arctangent. That was easy. And I can even use this series to find a series without an x, just a general series that converges to pi. Remember that arctan of 1 is pi over 4, so I plug in 1 for x. Let's do that to the other side. So if I plug it in there, I should plug it in there. And I get 1 minus a 3rd, plus a 5th, minus a 7th. If I multiply by 4, I get a series for pi. And this technically is pi. This goes on forever, adds up to pi. So why do we not know every digit of pi then? Well, this converges really slowly, and there are other ways that computers can do that are faster, and we're in billions of digits, but we're never going to find them all, right, because pi doesn't end. But this is a pretty cool way to get a fraction that's a really good estimate of pi by just taking some of those terms out. All right, so that's one way. Another series that we know using geometric series is just the standard geometric series, right? If a is 1, think of a over 1 minus r, except we're using x. And that's going to converge only when x is less than 1 in absolute value. So same idea as the other one, right? These are geometric, so from minus 1 to 1. If I integrate both sides of this equation, let me block this off, I get ln of 1 minus x, absolute value, But notice there's a negative here, so I should have a negative up front. Remember back when we did partial fractions. On this side, I get to use the power rule again, which is the real easy part of this. X squared over 2, x cubed over 3, and so on. And now I want to check the endpoints, right? So the endpoints didn't work before. Let's check them now. 13 says at the bottom, let's plug in 1 to this series. And you get minus ln of 0, which is bad news because you know that ln of 0 doesn't exist. You also know on this side, if you plug in 1, you get the divergent harmonic series. Don't forget that ln of 0, that's really a limit, but the function goes to minus infinity, and then the negative up front makes it positive infinity. So you kind of get infinity on both sides, which is bad math, really, but it makes sense, right? On the next page, I'm going to keep writing on the page you're looking at, but we'll see at the top of page 38 in the workbook. Let's try plugging in minus 1. Well, you get negative ln of 2. On this side, you get minus 1 plus a half minus a third plus a fourth. The negatives are backwards, but that's the alternating harmonic series. If you multiply both sides by minus 1, you will get ln 2 equals the series that, remember, I rearranged this and showed you it could add up to anything, but I said it normally adds up to ln 2. Now you hopefully believe me. The other thing you should notice is that when I integrated this, one of the endpoints now converges. That didn't happen before. So when you integrate or differentiate a power series, the radius will not change, but the endpoints might. We're not going to hit that too hard, but that's just an important fact that you might find useful. All right, so if you go to where 14 is on the next page, there's one last thing for this lesson, which is the Plicker's wrap-up. And so we want to talk about when these series can converge or diverge. And so we have a general power series. You should tell just by looking that the center is 0. Okay, so let's draw a number line here, 0. At 7, 4, 5, 6, 7, it diverges, so I'm going to put an X there. And at negative 3, it converges. A check mark there. So remember that I said that series radius of convergence is always symmetric around the center. So if it works all the way to minus 3, it should work up to 3. Now, I don't know what's going on over here. It could stop at 3. It could go all the way up to 7. But I know that it's not going to do this and then have stuff later. That doesn't make sense. Okay, once it stops, it stops. So maybe it goes all the way to 7, but it's not going to go past 7. 7 might be the endpoint that's open. Maybe the whole thing stopped at 3, but it's not going to go to 9, right? Definitely not to 9. Nothing past 7. Well, they're asking about negative 9. 4, 5, 6, 7, 8, 9. But remember that this whole concept is symmetric around the origin. So negative 7, I don't know, because that could be like maybe an open endpoint and a closed endpoint for 7 and minus 7. But minus 9 definitely won't work because this thing is always symmetric around the center. The center is 0. If 9 is no good, minus 9 is no good. If you're right at the edge that you know, that's different. But I know that the radius, just from this part here, I know the radius is less than or equal to 7, not 9 or 8. All right, so the answer then is that at x equals minus 9, the series actually does diverge. If they had said negative 7, it would have been C, because it could have been an endpoint. But you know that once you get to 7, you got to stop in both directions. You may have thought D, but now hopefully you do not. All right, let's stop there. See you guys next time.